Okay, so please excuse my still kind of croaky voice. So we got a bunch of announcements for today. Quiz number 5 is this week. So this is going to cover everything up through last Friday's lecture. So all of Chapter 7's fair game, guys. And also the first part of Chapter 8 up through naming almost all of ethers and sulfides. Then the Chapter 8 sapling is open now. It's going to be due Monday next week, 9 a.m. And our exam review is next Sunday afternoon, 3 to 5 p.m. in Duane G1B20, like always. That's going to be lecture captured, so if you can't make it, you can still see what questions were asked and what the answers were. And then our exam is a little over a week from today, 7 to 9 p.m. in Chem 140, same as before. Any questions about that? Yeah?
What would the exam cover?
So everything up through the Monday the day before. Based on where the syllabus schedule has us, we're about 1 lecture behind. I've caught up a little bit from the snow day. But it still remains to be seen if we'll do all of Chapter 9. I may cut out like the last couple of reactions at the end of the chapter that are kind of different from the rest of the chapter. So we'll see how we go. Hopefully we can cover everything else up through that, but I'll let you guys know the cutoff, hopefully the Monday the day before. Okay, any other questions about that? Okay, cool. So we've done a whole bunch of naming the last couple lectures. We're almost done. I just have one last naming thing to cover before we get into other stuff for this chapter. So non-systematic cyclic ethers specifically. There's this entire separate system for naming rings with different heteroatoms in them, either oxygen or nitrogen, or both. But we're only going to cover a few of them, and some of them you already know. All right, so let me actually draw 2 up here. All right, does anyone remember what this one is called, or what abbreviation it goes by? Yeah, CHF. Good. So that's THF. It's a solvent that's really commonly used. Now that we know a little bit more about ethers, we can see that this is actually an ether. It's got an oxygen with 2 R groups on it. Those R groups just happen to be joined together in the back. So THF is short for tetrahydrofuran. So it's furan, this guy here, with 4 hydrogens stuck onto it, which is getting rid of those 2 double bonds. Okay, so those 2 you've already seen, but those are a couple of common names that are helpful to know. Since we're doing a lot of like oxygen and sulfur equivalents in this chapter, we may as well cover the sulfur equivalent of furan, which happens to be called thiophene. So that one will sometimes pop up. And then a couple more. This one is dioxane. It's useful as an organic solvent. It's also pretty bad for people and the environment. I think there's been a few cases of this getting spilled in large quantities and causing a whole lot of problems. And then this one, the name for this compound itself, specifically a ring with an oxygen, a CH2, and a CH2, is actually oxirane under the naming system for rings, Hansch-Widman. But this is one example of a specific type of ether that's cyclic, but also just a 3-membered ring. So oxirane is the smallest example of an epoxide. So an epoxide is anything with a 3-membered cyclic ether in it, this ring with carbon-carbon oxygen. But most of the time they'll see like other R groups hanging off one or both corners. All right, so most of Chapter 11 is actually about epoxides, so I'll dip back into those later, but just to introduce them now. Okay, so epoxy-based superglues are actually have to do with this functional group because the ring can open pretty easily, given that it's a 3-membered ring under ring strain. It wants to sort of stop being a 3-membered ring. Okay, any questions about those Unfortunately, we're not going to go into the system that sort of describes how these names get applied. It's just sort of, these are a few common ones you may see. I'm not expecting you to, excuse me, draw the structures from scratch, but God dang it. But you may, I guess, need to recognize them occasionally. Okay. So that pretty much wraps up naming for this chapter. The rest of what we're going to cover is a little bit more of degrees of unsaturation, and then we'll get into physical properties. Okay. All right, so we covered degrees of unsaturation for hydrocarbons. In chapter 2. So remember that the formula for saturated hydrocarbons the formula is going to be CnH2n plus 2. And then each pair of missing H is 1 degree of unsaturation. So now that we're starting to look at stuff with heteroatoms in it, how do we describe degrees of unsaturation? Those of you who've taken lab, you've already seen this a little bit, but okay, so how to handle heteroatoms. Easiest way, like there's other more complicated versions of the equation that you can use to calculate it out based on how many carbons, H's, O's, N's, and halogens. But the way that sticks the most easily, I guess, in people's memory from my experience is learning how to convert them to an equivalent hydrocarbon. Okay, so this is sort of based on knowing like equivalent connectivities. So for example, halogens only connect to one other atom when you're in a stable neutral molecule, same as hydrogens do. So at least as far as like degrees of unsaturation are concerned, halogens and hydrogens are completely equivalent. So what we're just going to do is replace all halogens with hydrogens in the formula. So if I'm starting with the example formula of, say, C8, H8, NO, Br, I'm just going to turn that Br into one more H and turn it into C8, H9, NO. Okay, any questions about how or why I'm doing that? Okay. The next step is oxygens have a total of 2 bonds, so when they're stable and neutral, which turns out that you can have a bunch of oxygens in your formula and not actually change the degrees of unsaturation. So for example, well here, let me write the rule first and then I'll show like how that might work structurally. Okay, so pretty much we can drop all the oxygens. So for example, if we had CH3OCH3, this oxygen here only has 2 bonds to it. And we can just sort of imagine, like if we had a model kit of this, just popping it out of the middle of the structure, sticking the 2 CH3s together, and we haven't changed any of the degrees of unsaturation. So structurally, we're fine to just remove all of the oxygens. You may be asking, what if I have an oxygen that's double bonded to something? And then in that case, you'd end up with a carbon with 2 missing bonds. Then you would end up having to shuffle some other stuff around, but you'd still end up with the same degrees of unsaturation in the long run. Okay, so for our example formula, C8H9NO that we have at the moment would become C8H9N. Okay, so questions about that? Okay, cool. So then the third step is dealing with the N's. This is probably the most complicated step. So the rule is for each N, we're going to remove one N and one H. And so let me show the example first, and then I'll show structurally how that might look down here in a second. So C8H9N, we're going to pull out one N and one H. So C8H8. The reason that works structurally is, imagine you've got like CH3 and with an H on it, CH3, because remember, nitrogen wants to have 3 bonds when it's stable and neutral. So if we just take this NH subunit, pop it out of the middle of the structure, kind of like we did for O, we're doing the same thing where we retain the same degrees of unsaturation. And again, if your nitrogen was double bonded or if it had a bunch of different R groups coming off of it, we may have to shuffle some other stuff around to get a structure that makes sense. But in the long run, we're not changing the degrees of unsaturation by doing that. Okay, so we end up with C8H8. And from here, we can just figure out our degrees of unsaturation like we would if it were a hydrocarbon all along. So okay, so C8 should have how many hydrogens if it's fully saturated? So 2n plus 2 gives us 16 plus 2 is 18. So C8H18 is saturated, which means that C8H8 is missing 10H, which gives us, 5 degrees of unsaturation. Okay, so C8H8 has 5 degrees of unsaturation, which means that all of the intermediate forms plus the initial starting structure of C8H8 and OBr all also have 5 degrees of unsaturation. Okay, so this can be pretty useful if we're trying to figure out a structure, especially if we're using NMR. Those of you taking lab, you already saw this like a month or so ago. But it is also useful for just sort of keeping track of, how many degrees of unsaturation you might have in your structure when you're trying to sort of look at changes during reaction. Okay, so questions about that? Yeah.
The long formula still functions.
Yep, yeah, if the long formula works easier for you, then use that. It's just, at least it seems to sort of fade out of people's memory a lot quicker than this procedure, which feels like it makes a lot more sense intuitively to me. And to be honest, I don't actually remember the formula off the top of my head. I'm sure you could figure it out from doing these steps, but I never use it. I just do the procedural way. So, okay. All right, so that's sort of a quick return to something that we saw a few chapters back and applying it to stuff that we're seeing now. So for the rest of this chapter, we're going to be looking more at structure and physical properties. Okay, so we've looked at a little bit of physical properties for hydrocarbons. So we know that no matter what the molecule is, the stronger the intermolecular forces are, the higher the boiling point's going to be. So stronger intermolecular forces always equals higher BP. I guess I should specify intermolecular forces in liquid form, which is what we're going to be in for most of this chapter. So that's true no matter what we're looking at. Just the more strongly these molecules stick together, stick onto each other, the more energy you're going to have to pump in to make them let go of each other and go off as vapor molecules. Okay, so turns out that, say we're comparing a hydrocarbon, say like cyclopentane, which happens to have a boiling point of 49 degrees C. If we now swap to something with a heteroatom in it, say like THF here, almost the same structure, pretty close to the same molecular weight too. Just that one small change takes our boiling point up to 66 Celsius. All right, so what's going on here? Turns out that so we know that these bonds have a dipole where the carbon-oxygen bond is polarized towards oxygen. So the CO bond is polar, and that's giving us an overall dipole in the molecule. So within each THF molecule, the CO bonds are pointing that way, which means that we can draw an overall dipole for the whole thing of, in general, the back end of the molecule is delta positive, and or I guess the top end, the way I've got it drawn now, is delta positive, and the bottom end with the oxygen on it is delta negative. So I guess you can also sort of look at dipole induction. We know that it sort of gets passed along through the chain so that maybe these carbons are delta positive, but they're passing along some of that to the ones in the back as well. Okay, so this whole thing has delta negative on bottom, delta positive on top, which means that if it happens to line up with a neighboring one that's pointing the opposite way, you're going to get some attraction between the delta positives over here and the delta negatives over here, and vice versa. The delta negative over here is going to be just a little bit stabler and happier being in proximity to that delta positive on the other molecule. So you can get these long chains of sort of alternating THF molecules where it goes like oxygen on top, on bottom, on top, on bottom, where they're all stabilizing each other by alternating polarities. Okay, so that's one factor that contributes to intermolecular forces, is just sort of dipole attraction. Okay. So that's going to increase our BP a little bit. Okay. So it turns out that there's actually an even stronger intermolecular force that we can look at in some of the molecules in this chapter, which is not just based on dipole interactions, it's based on something that's almost in the direction of being a true chemical bond. Question?
Does this kind of attraction constitute heat from like a layer or lattice?
Good question. I think any sort of like larger structure, like crystal-like sort of packing, is really short-lived, and I don't think it's like any sort of actual like liquid crystal like layering thing. I think it's just sort of a really transient thing, kind of like water molecules, where they will prefer to like line up a certain way, but they never stay in position for very long. So I'll actually cover water molecules doing their thing in just a second here too. Any other questions about dipoles before we move on? All right, cool. So for water and ROH, we can get an even stronger intermolecular force. And that is hydrogen bonding. Okay. So it's kind of like a general schematic for how this looks. The way we need to have hydrogen bonding set up is we have an R group with some XH functional group on it. And that's attracted to another R group with its own Y functional group on it. And so it's not a true chemical bond that's being formed. Think of this as sort of like a proton transfer reaction, like an acid-base proton exchange that gets like a little bit of the way forwards and then stops when the H is sort of split partway in between these two atoms. So so proton transfer that stops partway. So it's a lot stronger than any of these intermolecular just electrostatic interactions, but it's not as strong as an actual like covalent chemical bond would be. Okay, so X and Y are usually nitrogen, oxygen, or fluorine. Sulfur can actually hydrogen bond just a little bit too, but it's much weaker at it. We know already that sulfur is kind of a weaker base than, say, oxygen is, which is above it on the periodic table. And so it's sort of less good at doing proton transfer. Okay. So to describe sort of the different roles that are being played here, we're going to call X in this case the H bond donor. It's the one donating the proton, at least partially. And Y is the H bond acceptor. And note that Y has to have a lone pair in order to do this. Otherwise, there's nothing to go out and attach the H, or attack the H. All right, so we know that hydrogen can only have a total of one full bond at any time. So if you think of it as like, maybe this is 10% of a covalent bond. I don't actually know what the numbers are on average for H bonds, but that seems about right. So if that's maybe like 10% of a covalent bond, we know that this XH bond over here is getting weakened correspondingly. So this would have to be about 90% of a covalent bond. So by partially attaching Y onto the H, we're sort of like slightly detaching the X on the H from the X at the same time. So if you're taking lab, you may remember that things that hydrogen bond usually don't couple to any of their neighbors on R. This is kind of why they're sort of like partially detached from the molecule already. They're not really getting enough of an influence from the rest of their molecule anymore. Okay. All right, so we know that water can be both an acid and a base. It can be a proton acceptor and a proton donor. Turns out this works the same for H bonds as well. So they can do both roles. So what you can get are these long chains of water molecules that line up with the hydrogen from one, forming a partial attachment to the lone pair on the next, whose H forms a partial attachment to the lone pair on the next. It bonds to the next and to the next. And I'm only showing this one directional or like one-dimensional, but both of the H's on a given oxygen can do this at once, so you can get these huge branching structures. But they're always pretty transient and temporary because these H bonds can sort of form and break very easily. Okay, so some molecules can do one role but not the other. So for example, ethers can be H-bond acceptors, but not donors. So they can't H-bond to each other, but they can H-bond to something else that's an H-bond donor if you throw it in there with them. So again, maybe showing THF here. This can't really do anything with another molecule of THF as far as H bonding goes. But as soon as you put THF and water in together, that can form an H bond, and these things can get a pretty decent intermolecular force going on. Okay, so hydrogen bonding is the strongest intermolecular force. And so it's going to raise boiling points by a lot. So if we throw up 3 molecules here that all have pretty similar molecular weights, let's look at ethanol, dimethyl ether, and propane. All of these are really similar weights, but this one has hydrogen bonding as its strongest intermolecular force. This one only has dipole-dipole interaction as its strongest force. And this one has nothing but just van der Waals, like temporary dipoles. Okay, so this one has H bonding, plus it also has the weaker 2. H bonding, it's also got dipoles, and it's got van der Waals, because everything has van der Waals. But H bonding is the strongest force going on there. Here, it's got dipoles and also van der Waals, but dipoles is the strongest force. This one is just van der Waals. Okay, so boiling points of these things. 78 Celsius for ethanol, negative 24 Celsius for dimethyl ether, and negative 42 Celsius for propane. So a huge difference there, over 100 degrees, just by throwing some H bonding group into the structure instead of just all hydrocarbons. Okay, so questions about those? Okay, cool. So, what this means for us in terms of actual physical applications in lab. So we've looked at a few cases of solvents being used for reactions, but we haven't really talked about like why we would pick a particular solvent yet. Okay, so most organic reactions are done in solution, which means that not only do you have the molecules that are actually reacting with each other, you also have some usually unreacting, but sometimes reacting, liquid molecule that's just sort of surrounding and mixed in with all the actual reagents and reactants and sort of just keeping them in contact with each other. So solvents are just a liquid used to dissolve reagents during a reaction. So it turns out that the choice of solvent is actually going to strongly influence not just like how fast the reaction goes, but also whether it works at all. Okay, so there's 3 major ways that we want to sort of split things up into groups here. So ways to categorize them. So first of all, we're going to look at what's called protic versus aprotic solvents. This is just another way of describing, is it an H bond donor or not? And if you look at the name, protic means it's got protons that can come off pretty easily, which we know is sort of a factor in H bonding. Okay, so this is probably the biggest effect on whether a reaction works or not. There's a lot of reactions that straight up will not work in protic solvents, like having H's around immediately kills off the reagents that you're trying to use. And we'll see some of those in the next chapter. So protic or H bond donors, the most common in that category are kind of like we saw up here, water and ROH. One other category that also counts is carboxylic acids. So anything with this R, C double bond O, OH, also has an OH group that's can donate a proton. And then one other that I'm just noticing I didn't list in the notes is any sort of amine as well. So R and H2, also an H bond donor. Not very commonly used as solvents because they smell a lot. Okay. Most others are aprotic. Okay. So a few common examples, I didn't list them in the notes, but like some that you might see real frequently are, say, acetone, or DCM for dichloromethane, THF, also not a proton donor, or a protic solvent, DMSO, DMF. Pretty much if something goes by an acronym, you're probably pretty safe to assume that it's aprotic most of the time. Okay. So questions about those so far? Yep.
Just kind of going back a little bit, but you have like the temperature formula for amine, NH2.
Uh-huh.
Is the NH2 always like a terminal?
No, so I drew for an example a primary amine here, but yeah, you're right. I could also have drawn like specifically like R and H, like a secondary amine or a tertiary amine. Okay. No, actually, I could not have drawn a tertiary amine. Why is that? Yep, yeah, there's no H that could come off of it. Yeah, so it's got to be primary or secondary. Good question. Okay, I think I saw another hand come up over here a little while ago. No? Okay, any other questions about this part before I move on? Okay, cool. All right, so this is sort of the biggest divide between solvents is do they have an H that can come off pretty easily? Because that can really screw up whatever acid-base chemistry you're trying to do. If something's just like, here, have a proton, and you're like, no, I didn't want that, which is actually really going to be a frequent problem for a reaction that we'll see in the next chapter. Okay. So another kind of way of subdividing these is polar versus nonpolar. Okay, so I know we've talked about polar molecules before, things with the dipoles. Just to really screw with you, this is actually referring to a totally different type of polarity. So it's not the same thing as having polar bonds. what this means when we're looking at bulk properties of a solvent is something more to do with sort of electrical behavior in the bulk. So this covers whether it has a high dielectric constant or not. Okay, and those of you who are taking or have taken whichever physics course covers electricity and magnetism, this hopefully rings a bell. But the whole deal here is that some solvents are a lot more effective at shielding electric charges from one another, and some pretty much like don't shield them at all. So I'll show kind of what that means in a second here. But there's a whole table like that takes up most of a page in Loudon that has like a whole bunch of solvents, whether they're protic or not, whether they're nonpolar or not, and then also what their dielectric constant is. And that's just kind of arbitrarily chosen to be, so the dielectric constant is that, I forget, I think that's an eta? I'm not completely sure, but someone correct me if I'm wrong. But so the dielectric constant is going to be 15 or lower to be considered nonpolar. Okay. So what this means as far as like how you're actually going to measure it and what it means for our molecules more importantly, if you just have like two ions floating around in a vacuum, these two things are going to feel like a particular force towards each other that's just based on sort of the laws of physics of like how strongly charges pull together based on some physical universal constants. So vacuum or very low dielectric constant solvent, very nonpolar in other words. The charges are feeling the full force of their pull towards each other. Sorry, that's a little messy there, but full force of attraction. Okay, so what we're doing with a higher dielectric constant material, like a polar solvent, for example, something with E over 15, is basically these solvent molecules are getting in the way and sort of blocking these things getting at each other. So whatever these molecules look like, they're making it so that even at the same separation, these two ions are only getting pulled together a little bit compared to before. So a high dielectric polar solvent means lower force between ions. Okay, so we know that a lot of the reactions that we've seen already involve things with positive and negative charges getting formed, so like carbocations, halides, bromonium rings, that sort of thing. It sort of makes sense that how well those reactions go is going to partially depend on how strongly those charges are getting pulled towards other charges while they're existing, and how quickly they're sort of getting forced onto negative charged ions, or whether they're getting sort of blocked or interceded a little bit by the solvent molecules. Okay. So questions about what's going on there? Okay, cool. So one sort of warning is that oh, and I guess first of all, let me mention that you're not expected to memorize sort of the dielectric constants for any given molecule. And in fact, it's actually kind of hard to predict from structure. So let me actually erase the board and then I'll show an example. So I'm not expecting you to memorize which molecules are polar or nonpolar. And it's also quite difficult to figure out from structure because a lot of the things you would expect to be polar molecules are not actually polar solvents. So we're looking at two different things here. So for example, acetic acid looks like this. Okay, so we're looking at this. There's a pretty strong dipole on both of the CO bonds. We'd expect that to be a polar molecule, but it turns out the dielectric constant for this thing in the bulk, you pretty much just have to measure experimentally. There's no good way to predict it from structure unless you're doing a bunch of fancy computational chemistry. But its dielectric constant is actually real low. It's a nonpolar solvent. Okay. So unlike protic versus aprotic, which you definitely can figure out from the structure if you know it, this is just sort of, you got to measure it in person or read the data from someone who has more frequently. Okay, so how this affects our reactions is a little bit more subtle, but it mostly has to do with how strongly charges get attracted to each other, of course. But it also has to do with, polarity in general affects also how well a solvent is going to dissolve different things. Okay, so if we have some kind of ionic solid, we looked at these real briefly in chapter 1, but you should also hopefully remember it from Gen Chem. If we got some grid of like positive and negative ions in a crystal structure, so like this, if we bring in some solvent molecules and start trying to dissolve this, what's initially going to happen is that we're not just going to split this whole thing up into completely disconnected ions. What we're first going to do is split it off as ion pairs that are surrounded by, let me draw these slightly shaded ovals. Actually, here. So this is called dissolved ion pairs. So initially, you're sort of keeping the positive and the negative charges together. And if you continue to sort of dilute the sample down or give it sort of more incentive to split up, you're going to get dissociated ions where each individual one has its own separate container or solvent cage of solvent molecules around it. Okay, so this would be dissociated ions. Okay, so where the equilibrium lies for each of these two steps, solid going to pairs and pairs going to completely split up dissociated ions, kind of depends on how strongly they're pulling on each other once they're in these separated states. So like the more effective these solvent molecules are at blocking the force they feel, the less likely this pair is to get back together and continue being a dissolved ion pair. Okay. Yeah.
Form specific structures like micelles or?
So that's a little bit more complicated. We'll get into that Actually, I guess not till Chem 2 when we start covering carboxylic acids. But yeah, that has more to do with like dissolves like, which we'll cover a little bit after this section. So, yep, good question. Okay. So any other questions about what's going on here with polarity? Okay, cool. So one last thing in the last couple minutes that I got left is donor versus non-donor. And this is basically just, does it have a lone pair that it can donate easily? Okay, so anything with an oxygen in it is going to be a donor. Anything with a nitrogen with a lone pair. Okay, so note this is not the same thing as being an H-bond donor or not an H-bond donor. This is looking at lone pair or electron pair donation. Okay, so some examples are ethers, alcohols like ROH, H2O, and amines. Okay, so that is actually a good place to wrap it up. So I'll finish like the last little quarter of a page on Wednesday, and then we'll get into chapter 9. So I'll post the chapter 9 notes today as well.
Dr. Richardson, the